Thank you for your kind invitation. I mean, coming in Poland every time is a pleasure. You're excellent hosts, excellent scientists, and this event is very, very impressive. I'm very, very happy to be here with you. Thank you for the opportunity. So yes, exactly. The topic is consciousness, and we start by being very modest about it and admit that we don't know what exactly consciousness is. We all know that throughout the centuries, it has troubled the minds of philosophers. Several aspects, theoretical and philosophical aspects have been proposed, mainly checking the relation between the mind and the brain, leading to options like materialism, that the mind is the brain, functionalism, the mind is what the brain does, dualism, the mind has nothing to do with the brain. And we found this diversions in opinions in a survey we did some years ago in collaboration with Andrew, where we asked maybe students and young scientists whether they think that the mind and the brain do separate things, and the majority in Andrew, they were very undergrads, they supported this distinction, and like 1/4 would say that the mind is complementary to physical. Despite these controversies, we should agree that indeed the mind has something to do with the brain. And to define consciousness, it seems that we cannot really say that there is one thing that makes us conscious. We'd rather approach it by defining different dimensions. So this is a proposal that was put forward, like we have to define dimensions on different aspects of consciousness, like on cognitive functioning, like memory, this can be attention, language, and so forth. And depending on the intensity that is representing each dimension, we can define fingerprints. So this, for example, state could be a conscious state 1 that's different from conscious state 2, conscious state 3, and 4. So this is just a suggestion, and we're mostly going toward this direction. But before we have to answer this complex thing, let's make things very, very simple. So we have a common frame ground to communicate. So I invite you to approach consciousness as we do in the clinical setting, meaning that we can define it based on 2 dimensions, wakefulness and awareness. And hopefully, even after a really big party yesterday, I find you here, where you are awake and aware of what's happening around you and about yourself. And this, just to give you an example, that could be the transition from full wakefulness toward deep sleep. The less wakeful you become, the less aware you become of yourself and your surroundings. With the exception, of course, of REM sleep and lucid dreaming, where the brain seems to work at the levels of that we encounter during typical wakefulness. We have in this case the lock-in syndrome. These are patients that they're fully conscious, but their motor repertoire do not allow them to show that all the time. So in the case of the total lock-in syndrome, patients cannot manifest the preserved levels of consciousness. Nevertheless, they are conscious. And then this is in sharp contrast with what happens in coma and in general anesthesia. So we are supposedly unconscious because we cannot be awakened even after painful stimulation. What is interesting with this type of definition is the exceptions that they come from the clinics, from the so-called disorders of consciousness. And that would be the unresponsive wakefulness syndrome, classically known as the vegetative state, and the minimally conscious state. So these 2 types of disorders of consciousness that challenge us deeply, both at the scientific level, to see what are the neural correlates of consciousness, and the clinical level. What happens in the mind of these patients that they are unable to communicate by definition? So vegetative state patients, they classically open up their eyes. These are patients that they sustain severe brain injuries. So classically they would spend some time in coma, and when they come out, they will show different types of behaviors. So the vegetative state patients will open up their eyes, but they will show no behavior meaningful in terms of reflecting auditory, verbal, or motor significance, meaningfulness toward consciousness. And that's why they're considered unconscious. And then we have the minimally conscious state patients who show more reflex behaviors. In the sense, like, if I have an object, or a mirror even, in front of them and I move it around, they will track it. Or they will respond differently to an overstimulation. It will be less reflexive. Yet, they will remain unable to communicate. If you work with this type of clinical population, immediately you will be exposed to so-called ethical, medical ethical issues that signify the moral significance of consciousness. The classic one is like, how do we approach the medical management of these patients? First of all, like, do they feel pain? And how can we know that in the absence of the communication abilities? So if during daily cares, a patient would show this type of reactions at the bedside, how would a nurse or a medical doctor would know that this is a meaningful response of pain? We asked, just to see how people think about it, we went to medical conferences, meetings, like here now, some years ago, and we collected opinions about people, how they think about these very challenging scenarios. So for example, here, I'll show you the results of the survey, almost 2,000 people answering to the question, do you think that patients in a vegetative unresponsive state, a minimally conscious state, can feel pain? And the majority agreed with pain perception in a minimally conscious state. Interestingly though, if you see, 60% almost, they would agree so also for the unresponsive patients, although this is a significant difference. And this goes against the classic definition of the vegetative state that has been proposed by medical consortia, saying that by definition these patients cannot have this type of experiences. And so, even so, we know that from cognitive neuroimaging. So here's just to show you, like, in a cohort of healthy controls who have received painful stimulation, I think it was a laser of the medial nerve of the wrist. You see the so-called pain matrix. So this is a class brain medial of different sections. And then we can see how the painful stimulation was processed in a widespread way, in sharp contrast with what happens in the brain of unresponsive patients, where the stimulation activated islands, encompassed islands of activation in the brain. And this is to be compared with what happened with the minimally conscious state patients receiving painful stimulation as well, that showed a similar to control activation after the painful stimulation, including the thalamus, the primary somatosensory insular, secondary somatosensory cortex, and the anterior cingulate, where it's not. So this at least gives us the impression that the stimulus was processed in a satisfactory way. So, but of course we cannot know whether these patients suffered from it or not. Another challenge is like what happens with these patients for the end of life. So we're talking here about limiting artificial nutrition and hydration. How would you feel if you had to limit the resources in patients, depending whether they were unresponsive, minimally conscious? And we did also ask this question to participants. And we asked this question in two different ways. So first, whether they agreed with treatment withdrawal, and whether they would like themselves to be to have a limitation of treatment if they imagine themselves in these conditions. So first, we found that people agreed with limitation of treatment both in a vegetative state, and they also thought like, okay, if I were to be in this condition, please, I would not like to be kept alive. But interestingly, when it was for the minimally conscious state, the majority disagreed with treatment withdrawal in general. But if they imagined themselves as minimally conscious, they would not like to be kept alive. And this points to the fact that consciousness carries some information, some moral significance. And when we asked, for example, how they felt about this condition in comparison to other states, if, for example, they had a vegetative state patient, they would think that this is worse than death, and that would be very relevant for the families. So families that they have this set of patients, they are not in good condition. But if the MCS was compared with the unresponsive, they would find that this is more relevant for the patient, suggesting that if you have some type of conscious or cognitive-related behavior, or like cortically mediated behavior, that is relevant for the son. So when we go to the bedside, I will show you what type of patients we're dealing. So typically these patients, they're very, very spastic. They have very low types of behaviors that we're trying to make sense out of them. This is a very, very famous case in the US, the case of Teishavo, that attracted the attention of the media, especially because the husband and her parents were in the court arguing whether they should limit hydration and nutrition in this patient. So what we do classically, how we can behaviorally evaluate consciousness, we do it by evaluating motor responsiveness and thinking that we are also this reflects cognitive capacity. So in coma, motor reaction is small. Once patients open up their eyes, they're supposed to be in a vegetative unresponsive state. And when they show type of awareness like command following or non-reflex behaviors, they're said to be in a minimally responsive state. And once we are able to establish functional communication, or when the patient shows that we can accommodate objects in a very meaningful way. So if I give a cat, they will try to drink something, or a comb to calm themselves. They're supposed to be conscious, and then efforts are made to go towards full recovery. But how reliable is behavioral evaluation? Depends on how we define it. So on the one hand, we are in need of standardized tools and assessments. I will tell you why. Because we checked those patients, a number of patients that came in our group with a clinical consensus of unresponsive vegetative state, okay? And when we checked them with a Coma recovery scale, the standardized tool, the classic one we do, only 18 that were in unresponsive. So 40% that were already misdiagnosed, and we could identify that with a standardized assessment. And then when we were asking, like, but is that the gold standard, really? We thought that it's not, and this was mainly because during our clinical practice, so typically we accommodate a patient for a week, and then during this week we have different sorts of assessment and batteries, and one of them is PET imaging. And we realized that in some patients, the metabolism of the whole brain metabolism was differentiated when it was in a unresponsive or minimally conscious state. So when we contrasted the standardized assessment with diagnosis based on PET, we found that even so, that the clinical assessment was unconscious, the PET was indicating the minimally conscious state. And this gives us a taste of how important neuroimaging and electrophysiology are for assessing the level of consciousness in these patients. And here we'll show you how we can do that by means of functional neuroimaging, specifically with functional MRI, because this is what I did. So in neuroimaging paradigms, specifically with fMRI, there are different types of ways to do that. We have active paradigms and passive paradigms. In the active paradigms, what you do is essentially evaluating command following by doing mental imagery tasks. So here we see how the areas that they're activated by doing two of these tasks, like imagine playing tennis, where we have the recruitment of the SMA, supplementary motor area, and imagine visiting the rooms of the house, parahippocampal place area. And these are tasks that they were activating the same areas in each and every healthy control subject during the validation period. And when we went to the bedside, we were able to evaluate with this paradigm 54 patients, and 5 of them, they had this activation, And even with one, we were able to use it as a brain-computer interface. So we coined this task as yes, this task as no. We asked questions. Interestingly, with this paradigm, although it can be very specific and it is not sensitive, in the sense like, if you don't do it, you cannot say that you're unconscious. Then we go for simpler paradigms, a passive paradigm, which is what I explained just before, where you exert an external stimulation and you measure the response of the brain. And an immediate limitation of that is that the setup, that it can be complicated in a clinical setting. So let's go for the simplest thing possible, and that is during rest. So you put the patient in the scanner, you record for 8 minutes, and you try to make sense of what you have out there. So that was my initial question, like, can we be useful for the clinics using the resting state paradigm? So what it means that the mind is at rest, really? It was proposed some years ago, of course, by Gillian James. You see, great ideas have been already said. So he actually observed that when we do nothing, our mind is like a stream of consecutive thoughts, like induced spontaneously. It's like watching something like an object, and then you have an associative thought with this, an associative thought with that, and so forth. So there must be some richness in this state of mind. And just to give you some numbers, the human brain is approximately 2% of the weight of the body. But a great deal of energy is used to support neuronal signaling. And only 5% of this energy is used for performance, for evoked, stimulus-evoked activities. So this means that while conscious awareness is inexpensive, it rests on a substrate which is very complex, dynamically organized, and most possibly non-conscious, that the brain gives very big of its energy to support. Let's see what we can do with that. So early on, it was found that the brain indeed intrinsically organizes itself in several types of networks and areas. So here, that was a seminal paper by Visual, that these are motor areas that they were recruited after a finger tapping task. And then he found that similar type of areas that were also recruiting during rest, spontaneously. And later on, more of this type of network level organization has been proposed, where we can see that the brain prefers to have clusters of activity. This is fMRI again. So it was found, it was an era where they were all talking about the default mode of function. And this was mainly suggested because they found, like, especially during PET studies, that there were some specific regions that they showed systematic deactivations during tasks. So you were doing a task, you were finding what you were wanting to find, but still, some areas they were showing deactivation at the same time. And these were suggested to be the default mode network of areas that they work by default. So if this is the medial part of the DMN, we call it like that for now on. And for example, if we are to measure the both changes across time, we find that even from these distant areas, the time courses correlate in a very high way. What was also observed, it was like the DMN not only organized itself within itself, but dislikes another network. In the case, like, when one is up, the other one is down. So they are decorrelate. So here, again, this is a percentage change of the bolt signal across time. Here we show the DMN activity. And here is like how another set of areas are decorrelating time. And these areas mainly encompassing frontoparietal cortices. This type of organization, we think that carries information about cognitive function. It's indeed interesting. So we were very keen to coin these two networks with a notion of internal and external awareness. Again, very simple way, but we want to make an argument here that the default mode network coined as a network of internal awareness, that is, whatever is self-related to me, autobiographical thinking, or envisioning the future, or recalling the past, and so forth. And the external awareness network, which is everything we perceive with our senses, all our environmental demands, and so forth. So, if we check, as I said before, the time courses of these two networks, they anti-correlate, and it's interesting to see that they switch their dominance on average every 20 seconds. Then we wanted to see what is the behavioral relevance of that. And we conducted a behavioral experiment, a behavioral neuroimaging experiment with healthy people. And we first started the behavioral task where we asked people to sit in front of a computer, place their two hands on a keyboard, where we coin right hand, let's say, external awareness, left hand, internal awareness, and then with every finger would represent the intensity. Not at all, a bit, a lot, fully. And we asked them to do, what we asked them to do is like, okay, we're going to give you a prompt, so from time to time they would hear a beep, and said, now, when you hear a beep, evaluate how you were before the beep, how much internally and externally aware of it. So they had to give 2 ratings. And we found that at the behavioral level, a similar pattern that we observed also during the time courses of during neuroimaging. And interestingly, we also found similar switching between the behavioral reports of external and internal awareness. Then we put them in the scanner. We made the scale a bit simpler, so this time it was from strongly external to strongly internal, and then we saw which areas correlated with these behavioral scores. So those responses that they were about strongly internally oriented, they recruited the default mode network. Those that they were externally oriented, the frontoparietal network. And with this way, we were more confident to say, okay, there is a behavioral cognitive significance of these resting state recordings. Let's push it a bit further. Let's validate this. Let's see how these two networks behave in a modified state of awareness. Ideally, you would like an anesthetized person to be able to respond, or like people in sleep to respond, but you cannot have that. So you need to induce a state of modified awareness that people are still responsive. So we thought to do that with hypnosis. And hypnosis was here induced as typically done in the pain center. It was done with an anesthesiologist who is trained inducing hypnosis for surgeries. And then we asked him, can you please help us trace a question here? So what we did, we had 12 subjects that we asked them, we scanned them 3 times during a normal conscious state, during a state where they did autobiographical mental imagery, and usually that was a pleasant experience ahead, like vacations, mostly in Spain. You know, Greece was maybe very popular. And then doing the same thing under hypnosis. So first we checked whether they were hypnotized. These are the classic dimensions that you do measure for hypnosis, like how much absorbed you are in the condition, how much do you dissociate yourself from the environment, and the amount of external thoughts you have. And people had to respond on a 10-point scale. So we saw that during hypnosis they reported a high rate for absorption, high rate for dissociation, and a small rate for external thoughts. When we checked functional connectivity, when it came to the default mode network, no big changes happened. What was immediately obvious was the modulation of the connectivity of the extrinsic connectivity network. And that was the connectivity in normal consciousness, and the autobiographical mental imagery, and this is what is not left during hypnosis, which suggests that in a modified sense of awareness, we can still measure this cognitive counterpart by means of functional neuroimaging. However, what is the effect of arousal, right? we deal with these patients. So arousal and awareness, they're here, that the components of consciousness, what would happen? We check that by doing an experiment with anesthesia, propofol-induced anesthesia. And among other things that we checked, connectivity changes across other systems, we were interested in the anticorrelations. So here is how the DMN during wakefulness, the anticorrelated system, and here how these anticorrelations tend to disappear on the propofol unconsciousness. So yes, it carries also information about the level of arousal. And then we said, okay, what is the effect of the environment? That was a great idea. Where are you going? That was a great idea. I was very, very happy to be involved in this experiment. That was really funky, in the sense like we were invited to participate in a parabolic flight. And those who are interested in body cognition, that would be a great condition to do, because during parabolic flight, what happens, I will give you a flavor here, is that you have a plane that follows a specific trajectory, right? It goes all the way up, and then it does this parabolic maneuver, and then essentially it's in free fall, right? So during these 21 seconds, you are floating around the plane, and then you're exposed again to a hypergravity condition. So these alterations between hypergravity, loss of gravity, and hypergravity again might change somehow your brains, even in long term. So we're all first-time participants in this experiment. We're scanned before, the day before, and then after the flight, we immediately run to the scanner. So of course, as it may sound, for the experiment, we try to see what we get. So we ran a voxel-to-voxel hypothesis-free analysis. And for those that are, again, interested in the body cognition, we found the right angular gyro that was modulating whole-brain connectivity. Actually, was participating less in whole-brain connectivity. We can see here that, we can see the insights here. And when we wanted to see which regions correlate, so when we use this region as a seed, we find that it predicts the full mode network in red and the anticorrelated in blue. And then we run typically the contrast pre-post flight, and the modification was found in the bilateral supramarginal gyri. So we see that the anticorrelations get less after the flight for both these sides, for the external extrinsic connectivity network. So yes, the way we are anchored in this world can also be reflected in this anticorrelated connectivity in the brain. And what happens finally in patients? So when we approach this problem to the patients, we first went for a sanity check, taking the DMN. Here we see how connectivity looks like across the patient groups: unresponsive, minimally conscious, those that exit the minimally conscious state and they are conscious, and healthy people. So we see that although there is a tendency for DMN connectivity to raise with the level of consciousness raising, still it cannot be differentiating between patients. And here we see that if we correlate MRI connectivity with PET metabolism, we see that there is a positive correlation as we approach healthy typical consciousness level. For the anticorrelations, contrary to our hypothesis that this would be meaningful to differentiate MCS from VS, actually, it was not the case, because but both groups, not only they did not show the anticorrelation, but they had hyperconnectivity with other regions. So the anticorrelations appeared only in conscious subjects, but not in non-communicating patients. And that was metabolically irrelevant. So here we see that higher metabolism characterizes the anticorrelations. So here this quadrant contains only healthy people and MCS MCS patients and no unresponsive people. subjects, suggesting that these anticorrelations are informative, they are biologically plausible behavior. However, still, my question was there, like, how can I use the resting state paradigm to differentiate minimally conscious from unresponsive patients? That was our main quest, right? So, out there, if you are doing connectivity studies with MRI, you would know that it's not only the DMN that has been suggested. As I said before, we have more networks that they are thought to reflect cognitive functions. They even given names, like we have the DMN, the executive control left and right, and the SANEX network with the insulas and the cingulate, mostly implicated in pain or conflict monitoring. And then we have sensory networks, like the sensory motor, auditory, visual networks, and we see that the visual system is quite complex as it comes in different types of subnetworks, and the cerebellum. So the question we had, the question we asked, like, how can I use this 10 network model to check individual patients? And let me take you by hand to show you how easy this is. So the first we have to do is to deal with severe deformations, right? So here, these are patient brains. You see there are ventricles, deformations, like strokes, and so forth. Then you have the fMRI recordings. And then you say, okay, let me do a connectivity estimation and check first the default mode network, how will it look like. So this is an outcome of independent component analysis, so we come right after to that. But just to show you that if you were to measure the properties of this component in these dimensions, actually reflecting the frequency oscillations of the time course from very, very low to very high, and how the histogram, what kind of properties it has. So if you see this fox-like thing, or like a bird, depends on how creative you are. So this would be a healthy component. So we see that in terms, especially in terms of time courses, because these oscillations are shown in the low frequencies, typically at this band. So in that case, if we go to the locked-in syndrome, we see that this is a satisfactory default mode network, and I would accept it as a healthy component. Let's see what happens in unresponsive cases. So here we have a case where the DMN comes only partially, like the posterior part. And I would say that this is pretty healthy because it picks at the right frequency band. But look at this. Would you accept that this is a healthy component because here I would doubt, like, because in terms of spatial properties, it appears okay, but it picks at very, very high frequencies. So how do we do that? What we suggest to do is to do independent component analysis. Are you familiar with independent component analysis? So just to wrap up, very, very simply, you have the World Cup where Argentina and Russia is the finals, and then you want to enter the court, but you cannot. So what you can do, or if you had the chance to see what happens in the stadium, is like, okay, can I use some microphones? And if you choose to use, let's say, 5 microphones, and you put them here in the stadium, there in the stadium, and there in the stadium, you could record different types of conversations and voices and so forth. But altogether, you would have, if you follow them collectively, you could follow actually the match, and you could see whether your team goal went and so forth. So the microphones would be your sources, and in that case, the stadium with all this noise, background noise, would be your fMRI signal, right? And then this is your fMRI signal. Then these are the sources that you choose to use, and this is what kind of conversations you get out of it. So you decompose it and you try to make sense out of it. Here we used 30 sources, and we, in order to get the right network, in terms of spatial and temporal properties, we first quantify how much each component, that would be the 30 components, would match the networks that we are interested in. So these are binary masks of the 10 networks. We estimated how well each mask would fit the component, and then by maximizing the goodness of fit, we would have an assignation of the components to the right templates. So in that case, a component that would be mostly not relevant would not be identified as a network, but this one would be. Or, and this would go on and on and on. And as the second criteria, selection criterion, we had the temporal properties where we trained the classifier to separate healthy, temporally healthy from non-healthy components. Here we check them as neuronal, non-neuronal. And why would we did that? We did that because we wanted to end up with meaningful signals to compare patients with. And in the end, out of the 10 networks, we ended up with 4 that were severely disrupted when it came to patients. So here we see the number of subjects showing the left executive control, right executive control network, the DMN, and the auditory, that these networks were nicely preserved in healthy people, but when it came to patients, we had severe underrepresentation. So for group studies, we entered only those maps that were found in the patients. So in that case, we ended up with a few number of patients. And then we checked for group level decreases in connectivity. And we see that these 4 networks, they all show connectivity decreases along the spectrum of consciousness. When we try to use neuronality as a feature to separate between groups, we found that this was a good feature only to separate patients from healthy people. So we had a good accuracy in terms of true positive and true positive rates in healthy patients. And the networks that made the difference was the DMN and the auditory. I will keep you that to the auditory to come later. For us, at that point, it was like, why a sensory system would come up to differentiate patients from healthy people? And by that time, we thought that maybe this is the case because patients are exposed in the noise scanner, right? You cannot cancel this. The initial question still remains. How can I separate MCF from unresponsive? It was really stubborn, I'm telling you. I wanted to show that to my supervisor. So I was like, okay, what I need a huge number of subjects I can use. So this approach, it can be insightful, but I don't have much of the power. What if I go hypothesis-driven and I replicate the networks by using seed correlation? So in that case, for each network here, I use areas from which I extracted the time course, I calculate the average, and I check for whole brain connectivity. So I have, in healthy people, again, the nice 6 networks. So I chose to have long-range connectivity networks, DMN, frontoparietal salience, and sensory-related, auditory, sensory, motor, and visual. First thing that we check is whether this reflects the level of consciousness, and we did that by correlating the behavioral scores. There was a Coma recovery scale, so the higher the scale, the more conscious you're considered, although this is not absolute. But it gives the first impression that the MCS patients here in blue, they had higher connectivity, this was correlating with behavioral assessment. Here we see that in green the unresponsive, and in coma, the comatose in black. Then we check, like, okay, how these two groups differ from each other in connectivity, and we came up with a set of areas. And we said, okay, but still, which of this network would make most of the difference? Which is the one that tells us about how to separate best? So what we did is, like, we treated this case as features. So we did a feature sorting, and we found that the auditory network was the one that was characterizing, was able to characterize 43 out of 45 patients accurately in our data set. Can anyone tell what would be the problem here if we stopped our analysis? Why would that be problematic? If I would say, okay, the auditory, 43 out of 45. So the problem here would be a double dipping, and we knew that. Double dipping because we already knew that these people would be different in these areas. I already know that. So if I go at the individual level, using this as a mask and extract the values, I would know that they are already different. And that's possibly why we have so high ratings in the classification. So in order to put us in an extra test, what we did is, okay, let's simplify things. Let's concentrate on the auditory that characterize the differences best. I would like to take it on different people. So we contacted colleagues from Cornell and Salzburg, and we asked for data. So different scanners. We had to trust the patient, the clinicians for their clinical diagnosis. So we had here, we see that we had 22 patients. The color would identify the clinical behavioral diagnosis. And here I show you the results of our classification. So we checked this pattern. So three features in that case. How could they predict the distinction between minimally conscious and unresponsive? Everybody who would be on that case would be MCS, here unresponsive. So out of the 22, we got 20 correctly, meaning that the machine, so what the brain says and what the doctor says, we agree. As a sanity check, we did generalize the classifier in healthy people. That was the demand of our reviewers that gave me almost a heart attack. I said, okay, just try to check your classifier in healthy people in the controls there. Under the hypothesis that there would be at least MCS. Yes, we did it. There you go. Unless, with the exception of 1.5 subjects here. Most possibly they fell asleep, but it's something to check still. So, yes, we are in a condition now to check how the classifier generalizes every week in our patient. We use that as information together with other imaging modalities. We're trying to make sense of what we see in these patients because, it's an ethical, I told you it's an ethical problem. The thing is that, just to give you a flavor about how connectivity informs us about the state of consciousness, but what does it mean for patients? What does it mean in consciousness itself? So this is a flavor of what we're doing in terms of dynamic alterations in connectivity. This is a huge collaboration with teams around the world. This is the consortium of the McDonald Foundation, and yes, it was funded twice. It was a long funding option. So here we use data sets coming from 4 medical centers around the world. So here would be Stephen from Professor in Liège, Professor Schiff from New York, Edwin Owen, he was in Cambridge, now he's in London, and Lionel Nakache from Paris. So what we found with my colleagues Enzo and Jacob, we cannot see anything. All the references are gone, and probably so much. You cannot see it. So, just to give you a flavor, I don't want to go into details about it, but when we check dynamic functional connectivity, we can come up with different states that would represent connectivity among regions, representing networks. Then we can end up with very complex systems, relationships of long-range positive negative connections toward very simple low connectivity states. And this would correlate very nicely with anatomy, underlying anatomy. And we saw that healthy people and minimally conscious state patients, they would most probably present this complex state, whereas this very simple state would be represented mainly in unresponsive patients. In any case, why does all this matter? Why we are so stubborn in doing so, right? It's fun. Do it. It's fun, really. Yeah, I mean, humans, we are inquisitive animals, right? We like to go further and further and further. Okay, come on. Just stop and think a bit. Like what we're doing, how this is meaningful. So some efforts in the past have been done to have an agenda of how we can use this information for patients. And then it's all about balancing costs and benefits. For example, like after a week, I have to show the results to the family that they came to us and said, please make an assessment, this assessment in our patient. Then I have to show the results. We have three scenarios. Then we have the tests that show less brain activity than neurological examination, higher activity than the examination, and they have the case scenario where everything agrees. And depending on the outcome, so here you can have like the relatives, if your tests show less stuff than behavior, the relatives may be able to take now decisions to limit life-sustaining treatment. Or they could lose hope if they were having higher expectations. In case that the brain activity is higher, then a good thing would be that we have now the chance to intensify our efforts for further recovery. But what if this is not correct, and then families end up having false hopes? And then you have the ideal scenario where everything is consistent, and then you have more realistic approach to the medical management of patients. A great benefit, however, from doing neuroimaging and physiology is for science. So here we see that with the passage of time and introduction of different states. So you know that the vegetative state has been also suggested as a medical error. You know why? Because up to the 60s, you would, if you had a cardiac arrest or an accident, you would die for apnea. But then you have the ventilator, mechanical ventilator to sustain your respiratory function. And only then we had the appearance of the vegetative state. So in that case, it can be considered a medical error. Just to say, just a thought. So with the passage of time, the use of those neuroimaging modalities, we were able to subclassify the minimally conscious state, for example, for plus and minus, depending on whether they show command calling or not. We can talk about functional lock-in syndrome, like patients that they can communicate by means of neuroimaging only, and also new names like cognitive motor dissociation, where a patient may appear unresponsive vegetative, but they can do command following with neuroimaging. What would be the benefit for the patients? We cannot ask them, I mean we can, but we can have no meaningful answer. What is the closest proxy? We can have people that have sustained brain injuries and they still find themselves in restricted conditions. That would be, for example, the lock-in state. So we collaborated with the Association of the Lock-in Syndrome in Paris. We interviewed patients and we asked them to evaluate their quality of life. And we cannot do that here. So what we asked them, and what you can also do with me, is to imagine the best period of your life, okay? And coin it with +5, let's say acceptance insights. And then pick it was the worst period of life and coin it with -5, like rejection from the local journal. And then you have to say, give us a number of how you've been there in the last week. So, okay, how many of you would think that lock-in syndrome patients would rate from 0 to -5? Wow, you know the study. You cheated. So indeed, the majority profess good quality of life despite their severe disabilities. Only a minority said that I'm leading a bad quality of life. And indeed, there is here a disability paradox. If we are healthy people, and if we think that we are patients one day, we think, how can we change? I mean, it's not going to be me anymore. But we are so resilient that the continuity of self-image continues even after a severe brain injury compared to what we think as healthy people. So, yes, let's give ourselves a chance to recalibrate our energies and our forces even when before we take decisions about difficult scenarios. When it comes to caregivers, the first thing we approached was the nurses, the medical staff, and so forth, and we checked whether these suffered some kind of burnout. And when they said, no, I don't feel burnout. But then we concentrate on those that they said, I did feel burnout. like mostly nurses and nursing assistants. And this is just the first flavor that dealing with these patients is not only about themselves and their families, it's also about the surroundings. And so what happens with families, we don't know yet. We have a great deal of data. We see these patients, these families every week. In the end, sometimes I feel that I'm morally obliged toward them because they are the ones that they carry all this burden. So in that case, doing clinical neuroscience, clinical research is about applying what you know about the human brain and how you can be helpful at the bedside. It's a kind of inspiration. It keeps you going. It's not like only about being rejected for funding. You can be helpful. So to conclude, fMRI resting state connectivity, I showed you that it can carry information about cognitive function, and it can be used in the clinical setting. And now we're in need of a framework when we combine it with the different other techniques to see how we can use them in terms of their availability, sensitivity, and specificity. And in the end, I would like to, and with the importance of thinking about ethical issues when it comes to dealing with these clinical populations, but just simply asking, what does it matter? What is important here? I would like to thank all of these people, really, each and everyone. Like, these are the team in Liège. These are people that, they're not in the picture, but still in Hague. International collaborators, the team in Paris. I would like to thank, of course, the patients, the families. I'd like to thank you for having me as a guest, as a female guest, as the only female guest. Well, I mean, it makes me feel like a Marie Sklodowska, really. Nevertheless, it's not hard feelings, just but the archives of history, because you know what to say, like, you learn history in order to choose your future. Thank you so much.
Okay, thank you so much. That's true. Your feministic conclusion was true. I think it was a great talk. We still have time for, I think, only one or maybe two questions. Let's say three, as you're only female here, yeah? What you say, okay? 3 questions?
You're the man.
Well, I say 3 questions. Okay.
So thank you very much, Athena, for this wonderful talk. I was curious about the potential mechanisms leading to the alteration of the default mode networks and how we can modulate the frequency of the switch. And it's possible at the top-down level to modulate that.
Top-down level, you mean like cognition, from cognition onwards?
Yes.
So with the hypnosis type, that was just indeed like a first flavor that this is possible. Recently it was proposed that it was a very nice paper about how the DMN can also contribute to automatic behavior. So imagine that you are driving or you're doing something very routine, action, so forth. Actually, in this type of behaviors, indeed, the DMN really shows a facilitatory contribution. It's there, especially with the hippocampal part that ignites your learned scenarios to support it. So it seems actually a very resilient network. You find it, especially the posterior cingulate, connectivity is very robust. The one thought is that this could reflect vascularization. So this is an ongoing thing. So indeed, this part of the brain is receiving quite a lot of blood supply, and yeah, the structure function thing is still ongoing. So to what extent this could be correlated to consciousness per se, I don't know. I think I'm doubtful about it. Yes.
My underlying thought was: is it like a dynamical oscillatory phenomenon, or is there like an active, because there's active disactivation of the DMN, so is there like an active process of switching the dopamine?
Active in the sense of
like controlled by other structures or other process?
So when they checked system level interactions, they found that it's not only itself that is driving the reallocation. So it was suggested that it's the salience that mediates the switch from the DMN to protoparietal activity, because the salience comes there and says what is salient, what is important. So it decides whether to engage this or the other. So yeah, in that case it was the first to be observed, but doesn't mean it's more important than others. Is that what you're asking?
Yeah.
Thank you. Okay, just a short announcement. We will start the clinical session right now after the questions here, but also in the second room. It's 103B. Am I right? B. Okay, 103B. And all the participants that are presenting their presentations over there are asked to go to the room 103B if it's possible. Yeah, we can go back to the questions right now.
Hello, thank you for the great talk. And I would like to ask about the possible application of these studies, like the whole studies that you made, to patients with to treatment with transcranial magnetic stimulation or electric stimulation in general, and how good predictor of the data that you have collected it could be for getting these patients awake.
So indeed, like neuromodulation and treatment options, we have been trying them. So there are different options. We have pharmacological, different agents. We have surgery, like the brain stimulation has been done in only one patient. And with our group, we tried TDCS, transcranial direct current stimulation of the dorsolateral prefrontal cortex. It was not miraculous. Of course, we expected something like that. So it did not work in the unconscious patients. But we had some respondents in the MCS group, but not to the point that they are waking. So the changes were very subtle to the behavioral scales, like they were changing a bit of the scale. So now we're trying to understand what kind of these neuromodulatory electric stimulations do at the physical substrate, not just with the behavior. And this is an ongoing project of my colleague, Optimal.
Okay, I'm partly referring to the study with waking up a person who were on ongoing vegetative state for 10 years or so, and researchers made to partially recover his consciousness via vagus nerve stimulation.
So that was a very recent study, right? And it received a lot of attention. I don't have much to say. I just checked the design really, because it was again one study of the patient of one patient, and I really wanted to see first the baseline assessment of the consciousness level, right? That's where you start from. I had the vegetative and evolved or not evolved. So I think it was just one evaluation. So I wanted to hear a bit more about how long this patient was evaluated for, by how many raters and so forth. But it gives for sure an insight, like it's a proof of concept of different approaches that we can have as modulation techniques. I don't want to be conclusive because I can't.
Okay, thank you.
Okay, one brief question, please. Okay.
Yeah, thank you for the very nice talk. I was wondering, are there any cases where epilepsy co-occurs with one of those states, so that you have the opportunity in a patient to record neural activity and see how that differs on a neuronal level?
Whether they've been having seizures during their recordings, you mean?
Yeah, I mean, in this only few occasions where you can record in humans neuronal activity, and so I was wondering, with like electrodes and really neurons. So I was wondering, and in epilepsy patients, that's now more and more the case when you try to search for the locus. And so I was wondering, does that sometimes co-occur with MCS, so that you can try to?
Yeah, epilepsy occurs